Hyatt Regency, Kansas City. On July 17, 1981, a routine Friday night tea dance turned into the deadliest structural collapse in American history. Inside the hotel's atrium, two suspended walkways hung above a crowded lobby floor, packed with dancers swaying to a live band. At 7:05 p.m., without warning, both walkways gave way at once, crashing down onto the people below. 114 people died. More than 200 were injured. What investigators discovered was a single change made months earlier on the construction site, not by an engineer's calculation, but by a steel fabricator's shortcut. The original blueprint called for one continuous steel rod running from the roof through both walkways, holding them in place like beads on a string. But running a single rod that long through both walkways during construction was difficult, so the fabricator proposed splitting it into two shorter rods instead. One connecting the roof to the upper walkway, a second connecting the upper walkway down to the lower one. On paper, it looked like a minor adjustment. In reality, it doubled the load on a single connection point that was never designed to carry it. The change was approved over a phone call that took less than a minute. Nobody recalculated the math. For over a year, the walkways held until the weight of a dancing crowd finally exceeded what that one connection could bear. After the disaster, two of the project's engineers had their professional licenses revoked. The case became one of the most studied failures in engineering history. 4 decades later, on the other side of the country, a different kind of failure was building, one nobody rushed to fix. Champlain Towers South Surfside. In the early hours of June 24, 2021, while most residents were asleep, an entire wing of a 12-story beachfront condo building gave way in seconds. 98 people died. The collapse wasn't sudden in cause, only in timing. Investigators believe that years before, water had been seeping into the concrete pool deck and underground parking garage, slowly corroding the steel rebar inside the support columns. In 2018, an engineering report had already flagged major structural damage to the slab beneath the pool deck and recommended urgent repairs. The full official investigation is still ongoing, but this remains the leading explanation. But the repairs never happened in time. The building's board spent years debating funding, gathering competing bids, and delaying the work, while the damage underneath kept spreading, unseen by anyone walking through the building above. By the time crews were finally preparing to begin repairs, the corrosion had already done its damage. Sometimes the danger isn't decades in the making. Sometimes it happens in real time, while the building is still going up. Hard Rock Hotel, New Orleans. On October 12, 2019, an 18-story hotel under construction suddenly buckled while crews were pouring concrete on the upper floors. 3 workers died, and the partially built tower had to stand, unstable, for months before it could be safely brought down. The investigation pointed to a sequence of construction errors stacked on top of each other. Several floor slabs had been poured before the levels supporting them had fully cured and gained their strength. At the same time, reinforcing steel inside those slabs had been placed incorrectly. Each issue on its own might have been survivable. Together, under the added weight of fresh, wet concrete being poured above, they triggered a progressive floor-by-floor failure. What followed was almost as harrowing as the collapse itself. 2 damaged construction cranes leaned over the wreckage, too unstable to approach, and had to be brought down using controlled explosions more than a week later. 2 of the 3 workers' bodies remained trapped inside the unstable structure for months as crews carefully worked floor by floor until it was finally safe to reach them. The last body wasn't recovered until 10 months after the collapse. Across the Atlantic, a renovation meant to make a building safer ended up making it deadly. Grenfell Tower, London. On June 14, 2017, a fire that started in a single kitchen appliance on the 4th floor of a 24-story residential tower spread up the entire outside of the building in minutes. 72 people died. The building had recently been renovated, and as part of that renovation, the exterior had been wrapped in aluminum composite cladding panels, chosen partly because they were cheaper than fire-resistant alternatives. Inside those panels was a combustible plastic core. Once flames reached the cladding, it acted like a chimney running up the side of the building, carrying fire from floor to floor far faster than anyone inside could escape. A public inquiry later found that warnings about the cladding's fire risk had passed through multiple hands, manufacturers, contractors, inspectors, and were missed or downplayed at nearly every step. Not every story like this ends in tragedy. Sometimes the flaw gets caught just in time. Citicorp Center, New York City. In the summer of 1978, structural engineer William Lemaitre got a phone call that would haunt him. A student researching his building for a class project pointed out a detail he had overlooked. Citicorp Center's distinctive design rested on 4 giant stilts placed at the center of each side, not the corners, necessary to leave room for a church below. Lemaitre had calculated the building could withstand straight-on winds, but the student's question made him check quartering winds, diagonal gusts hitting the building at an angle, and the math came back wrong. Worse, he discovered something he'd never been told. During construction, the contractor had proposed swapping the original welded wind-bracing joints for bolted ones instead, to save time and money. His own office had approved the change without flagging it to him. Lemaitre had no idea the substitution had happened until that phone call, months after the building was already standing and occupied. Under the right kind of storm, one with roughly a 16-year chance of occurring in any given year, those bolted joints could fail and bring the tower down onto surrounding Manhattan blocks. Lemaitre didn't run from the problem. He quietly informed the building's owners, and for several weeks during hurricane season, welding crews reinforced every joint at night while the building stayed fully occupied, averting a disaster the public never even learned about until years later. Other times, a flaw goes unnoticed for decades, hiding in plain sight until the day it finally gives way. A 35W Mississippi River Bridge, Minneapolis. On August 1st, 2007, during the evening rush hour, a steel truss bridge carrying 8 lanes of traffic suddenly gave way, dropping cars, trucks, and a school bus into the Mississippi River below. 13 people died, and 145 more were injured. The flaw had been there since the bridge was built in 1967. Certain steel gusset plates, the connecting pieces that hold the bridge's structural beams together, had been designed roughly half as thick as they needed to be. The error went unnoticed for 40 years. Over those decades, the bridge gained weight it was never meant to carry, added concrete barriers, resurfacing layers, and on the day of the collapse, construction equipment and materials staged directly on the deck. The undersized plates finally gave out under a load they were never built to hold. Aboard the school bus were 52 children and several adults, returning from a field trip. As the bridge gave way beneath them, the driver and a counselor got every single child out through the rear emergency exit before the bus could go under. All of them survived. In the years after, more than 100 bridges with similar design weaknesses were inspected, retrofitted, or replaced across the country, and for the first time, major bridges were required to undergo independent peer review during design, a direct response to a flaw that had gone unchecked for 4 decades. Not every failure needs 40 years to surface. Some take only a few. Big Dig Tunnel, Boston. On July 10, 2006, a concrete ceiling panel weighing several tons broke loose from the roof of a highway tunnel and crashed down onto a car driving below, killing a passenger. The tunnel was part of Boston's Big Dig, at the time the most expensive highway project in American history. The panels had been held in place using a fast-curing epoxy adhesive to anchor bolts into the concrete ceiling. But under sustained heavy load over time, that type of epoxy was prone to a slow, almost invisible failure called creep, the bond gradually stretching and weakening for years before finally letting go. It was the wrong adhesive for the job from the start. This particular epoxy formulation simply wasn't built to hold that much weight for that long, something investigators later said should have been caught before installation. The warning signs had already shown up 7 years earlier. In 1999, several of the same type of anchor bolts were found slipping out of the ceiling elsewhere in the tunnel system, but the issue was never properly investigated as a sign of a bigger problem to come. Prosecutors later said the company that supplied the epoxy knew its product wasn't rated for that kind of sustained weight, but never made that clear to the people building the tunnel. And sometimes the smallest incident exposes the biggest design flaw of all. Ronan Point, London. On May 16, 1968, a relatively small gas explosion in a kitchen on the 18th floor of a newly built apartment tower blew out one load-bearing concrete wall panel. It should have been a contained, survivable incident. Instead, the building's entire design turned a local problem into a chain reaction. Each precast panel had been built to rely on the panel below it for support, with no backup path for the load to travel if one piece failed. The moment that single kitchen wall blew out, every panel stacked above it lost its support in turn, and an entire corner of the tower collapsed floor by floor. 4 people died. The case became one of the most cited examples in structural engineering, leading to building codes worldwide that now require structures to survive localized damage without a full chain reaction collapse. If you like this video, subscribe for similar ones.